quantumlaserpointers.com.
Quantum Laser Pointers brings you the infamous double-slit experiment right in the palm of your hand. In 1801, English physicist Thomas Young performed this experiment to determine if light was a particle or a wave. A laser shines a coherent beam of light through a film disc containing two parallel slits. Light striking the wall behind the slits produces a classic interference pattern. This surprising result means light passes through the parallel slits not as particles, but as waves.
Visit our website or subscribe to our YouTube channel now. Be among the first to see our new line of double-slit lasers, quantumlaserpointers.com.
Hi, I'm Russell Leidick. I wanted to follow up from the previous video on quantum mechanics versus pilot wave theory in order to provide an improved explanation of the experiment. This presentation will not make sense if you have not seen that video, so a link is provided in the YouTube description. This is breaking entanglement from a distance, why the EPR paradox is so boring. So first of all, the EPR paradox, named after Einstein, Podolsky, and Rosen, describes the consequences of measuring a quantum system, also known as collapsing its wave function. In a nutshell, quantum mechanics appears to imply that entangled, that is, deterministically correlated, particles in superposition will always be measured, that is, observed, in a state which is consistent with the rules of that correlation, regardless of their distance of separation at the moment when any one of them is measured. Note that superposition implies that a given particle is in a mix of two or more discrete states, whereas entanglement implies that it has some deterministic relationship to the states of other particles. The correlation itself is chosen by construction, in the sense that the states of a subset of particles determines the states of the other particles. But beyond this guaranteed relationship, the actual states of particles is unknown until a measurement occurs. For instance, we might have 12 bits entangled in superposition, wherein the last 4 bits are the checksum of the other pair of 4-bit values. So for instance, the first 4-bit values might be 5 and 9, and the last 14, or the first 2 and 7, and the last 9. We won't know the state of the system as a whole until a measurement is performed, but we are guaranteed that the checksum will be consistent. Now, occasionally, quantum entanglements fail due to environmental noise, but in this case, we're assuming that such failures can be avoided for the short duration of the experiment. For example, look once again at this setup. We have a dual photon source. That is, it produces entangled pairs of photons, either both vertical or both horizontal. However, the bizarre implication of the EPR paradox is that they are in neither state until one of them hits one of these polarizing filters, at which instant they immediately decide to assume the same state. So it seems entirely reasonable to assume, as Einstein probably would have, that actually the photons knew their polarization state since their instant of emission. But it was later work by Bell, Clauser, and others that appear to demonstrate that in fact entangled photons behave as though they decide upon their state only upon measurement, whereupon they instantly convey that information to their peers in order to guarantee measurement consistency according to the correlation rules. So in this case, the correlation rule is that both of the photons have the same vertical or horizontal orientation. So at least conceptually, it's as though as soon as this photon hits this polarizing filter, it sends an instantaneous message to this photon to tell it whether or not to pass through. That is to say, whether to have vertical or horizontal orientation. Now, of course, one of these polarizing filters must be slightly closer to the dual source, simply because the distances are not exactly the same. So it turns out that we can easily fake a violation of the EPR paradox by modifying the apparatus in the manner below. Oh, and by the way, we can easily fake the outputs, that is these bits, if you will, of the original apparatus simply by making them equal, using an off-the-shelf computer, which should give some pause to anyone who hopes to rely on dual photon sources for the purpose of secure encryption key exchange. But that's another matter entirely. So here we insert what I call a random polarization selector in the right side path. When a photon enters the machine, its polarization is forced to a state which the machine had previously selected at random. The photon is then re-emitted. Now, apart from some additional flight time due to the presence of the machine, the photon arrives normally at the polarizing filter. However, at this point, the correlation has been lost, so that half of the time, the repolarized photon is oriented incorrectly with respect to its dual. So in this case, we might end up with a horizontally polarized photon, which will be blocked while its dual passes through. Now, anyone looking at only the polarizing filters would observe what appears to be a violation of the EPR paradox. But quantum mechanics actually predicts this loss of correlation because the machine here actually collapsed the wave function, and with it the entire entanglement, prior to forcing the new polarization. But let's see how pilot wave theory would deal with this. The entire apparatus is saturated with a single pilot wave. It's stable in some places, indicated here in blue, and unstable in others, indicated in red, with respect to the particular frequency of light which is passing through it, I might add. Now, most of the apparatus is permeated with stable pilot waves. By stable, I mean waves which might be changing with time, but are doing so in a straightforward, predictable manner. For example, some sort of sinusoidal oscillation. By the way, I'm not saying that the pilot waves are identical in these two regions, but merely that they're stable in both those cases. Now, inside the random polarization selector, the pilot wave is chaotic, whether or not the random numbers are being generated in the manner previously proposed. Why is this so? Well, because what amounts in quantum mechanical terms to collapsing the wave function actually involves massive instability in the pilot wave under pilot wave theory. If you think about it, the collapse would probably involve a very complicated collision between the incoming photon here and an atom inside the machine, sending phonons, that is crystal lattice vibrations, all over the place, only to subsequently interfere with the next photon to arrive and the next, etc. Nevertheless, we arrive at the same conclusion as in quantum mechanics, namely that the correlation between the photons is broken. While there is actually only a single pilot wave permeating the entire system, this region of chaotic oscillation has destroyed all evidence that the photons were ever entangled. Note that there is no measurement here, just a pilot wave storm, if you will, whose unpredictable and turbulent behavior has disrupted the experiment to the point of failure. So let's return to the original setup from a pilot wave perspective. Very shortly after the setup is constructed, a stable pilot wave will form, courtesy of photons and other particles coursing through the apparatus. It would be interesting if the first few photons emitted from the source actually violated EPR due to a lack of precursor photons of similar frequency. But I don't think that constitutes a valid test of pilot wave theory, because other photons in the room will have established some sort of pilot wave already. And furthermore, insulating the room would not help much either, because neutrinos might serve as pilot wave precursors. Who knows? It's easiest just to avoid these questions by construction. In particular, we construct a situation in which one of the filters, this one here on the left, is forced to oscillate at random between 0 and 90 degrees, that is, horizontal and vertical. We have, as before, three requirements. Number one, the filter must spend the majority of its time in either of these states as opposed to an intermediate state. Two, the decision of which state to assume must depend upon information which is guaranteed to never before have arrived on Earth. And three, the total time between the arrival of said information and the completion of any necessary rotation is much less than the time it takes for light to traverse the distance between the filters. In this manner, we should be able to form an unstable pilot wave in the sense that its evolution is non-deterministic, not merely chaotic. Now, as soon as we turn the rotator on, the pilot wave begins to destabilize, as you can see here on the left. But eventually, it saturates the entire apparatus. Reflections of the wave at various hard surfaces only compounds the instability. So in other words, if we make the rotator fast enough, and the length L long enough, then we should end up destroying the correlation between the photons, just as in the case of the random polarization selector. But wait! Quantum mechanics says this is impossible, because there is no way to destroy this entanglement by force other than by collapsing the wave function. But the wave function of a photon cannot move faster than the speed of light. So it cannot be influenced by the distant rotation of the polarizer over here. So the EPR paradox remains intact, and the expected correlation is discovered upon impact at either polarizing filter, assuming, of course, that the polarizing filter is at rest at that instant. So what really happens? So here we have Niels Bohr of quantum mechanics fame, and Louis de Broglie, who discovered pilot wave theory. What do we suppose they might have said? Bohr might have said, "So you think you can break entanglement by rotating a distant polarizer? Then the only thing broken here is your brain." And perhaps de Broglie would have said, "It is entanglement itself which is broken. Where does entanglement end and measurement begin? Why not just admit that space has a memory which creates this illusion?" So how can you help? Number one, do you know a physicist? Ask them about this problem. Be aware that they receive reports of perpetual motion machines, anti-gravity devices, and magic tinfoil hats all day long, so they may well ignore you. Failing that, perhaps your old quantum professor would have some insights. Number two, are you a physicist or do you work with them? Then please consider doing an experiment like the one in the first video. Good experimentation is worth much more than good theory. Number three, if the proposed experiment is not a valid test, then please explain why in the comments. Better yet, devise a better experiment and reply with your own public video. Number four, if you're not an expert but still think you have something to add, then by all means, please post a comment. Note, I cannot respond due to Google Plus issues, but you can also contact...
Visit our website or subscribe to our YouTube channel now. Be among the first to see our new line of double-slit lasers. QuantumLaserPointers.com.
Hi, I'm Russell Leidig.
Beam of light through a film disc containing two parallel slits. Light striking the wall behind the slits produces a classic interference pattern. This surprising result means light passes through the parallel slits not as particles, but as waves.
I wanted to follow up from the previous video on quantum mechanics versus pilot wave theory in order to provide an improved explanation of the experiment. This presentation will not make sense if you have not seen that video, so a link is provided in the YouTube description. This is breaking entanglement.
QuantumLaserPointers.com.
Quantum Laser Pointers brings you the infamous double-slit experiment right in the palm of your hand. In 1801, English physicist Thomas Young performed this experiment to determine if light was a particle or a wave. A laser shines a coherent